Hi, this is not really a tutorial, it's more like a guide. The thing is that I got a bit stuck on the subject of normals the last 2 weeks, and I want to share the solution for converting height maps to normal maps. Actually, the solution comes from shader graph in Unity. As a brief introduction, you should know that a height map is nothing more than a black and white texture that defines the shape of a terrain, where white is the highest value, 1, and black corresponds to 0, which means that there is no displacement. I am using noise in this case, but you can use a texture with real data. It's easy to find height data searching in Google, and it's free. But what is interesting in this video is to convert from a height map to a normal map. A normal map is a texture with vector information. The RGB channels correspond to X, Y, Z coordinates of vectors. It's worth to know that a normal points in the direction of the faces or triangles of a mesh. If this is not the case, you have to recalculate these normal vectors. Software like Blender does that by default. However, these operations can also be done by hand. In Godot, we have to use shaders. Now, the normal map allows you to have multiple vectors for each fragment. This means that a single triangle can contain multiple normal vectors, and these vectors define the way to reflect the light. So it's almost like having a high-resolution mesh to show small details. Just that we don't use vertices to represent details, but normal vectors. So how do we transform scalar information to vectors? Well, the process is not that simple because it requires the use of advanced GPU functions that use partial derivatives. Those derivatives return slopes to which we apply the cross product. Knowing this, it's better to use a tested and proven function, which we are going to take from shader graph in Unity, which is this one below. So I have converted the function to Godot, and here are the functions I mentioned before that obtain slopes between adjacent vertex positions or fragments through partial derivatives. This means that df dx and df dy are special because they break the parallelism imposed by the GPU in some way. Here is the cross product, and then the partial derivative functions are applied again, this time for fragments. In this example, I have a mesh with a high resolution that allows to apply a height map in a smooth way. As you can see, it requires a lot of resolution. In the following example, I get details but using a normal map. Actually, if you notice, the resolution of the mesh is not enough for that level of detail. I can even decrease the resolution of the mesh, and we can still see high resolution details thanks to the normal map. I get this effect just loading a normal map, which is a noise map with the normal option selected at the seamless checkbox. Now we will see the execution of the shader, which has a parameter of strength, the noise map, and the function using the variables and the coded constants. I can change the strength, and it has to be set low to be properly displayed. I can show the normal map by assigning it to albedo. And here is another example that makes an interpolation between two shapes, and I show it in albedo. There is also this example that simulates waves, and it looks pretty good. It's just a sine wave with polar coordinates, and finally I convert it to a normal map. You can see the normal map in operation. The last one is the same example but using Visual Shader. I made a custom node which is very easy to use. Just drag and drop. You can adjust the strength and set it to normal. Here inside are the functions for the shaders, and here is the custom node that has some parameters, and finally the same function. All the examples and the code will be available on GitHub.